Hey ChemExcel, this is the last video about the 5 factors that affect a rate of reaction. This one's going to be on concentration and temperature and their effects on collision theory. All right, so concentration. All right, I should know this from watching the demo video about would you mess with the concentration of your limiting reactant or your excess reactant. Okay, think about that for a moment. Okay. All right, should be thinking excess reactant, right? Limiting reactant, that adds other factors in there, like that's going to change how much product you're even going to make. All right, it's really hard to compare the rate of one reaction to another when you're talking about just using different quantities of materials in the first place. Okay, diluting a solution before using a reaction will make it react. Think about that. All right, faster or slower. Think about the reason why. Look at those 3 bullet points. Which one is affected? Okay. So we've got dilute solution makes it go slower because the molecules are going to collide less often. That's it. Has nothing to do with energy, has nothing to do with orientation. All right, packing more molecules into the same space or fewer molecules into the same space doesn't make your molecules align properly, so that can't affect the orientation component down here. All right, and it doesn't make them collide any harder or softer, so that's not affecting the actual energy of the collisions. It just means they can collide less often if it's dilute or more often if it's concentrated. All right, we got a little graph analysis here to kind of think about the course of reaction a little bit more too. It says what happens to the concentration of reactants as time goes on, right? So in this case, NO2 is the reactant. So we find NO2 on the graph and we can see what's happening to the concentration over time. All right, based on this, should reactions get faster or slower as reactants get used up? Think about that. The concentration is dropping. All right, what's that going to do to that rate of reaction? And if we look at where this is at the end, do we think that this is the end of this reaction? Yes or no? Okay, so think about that. Have a reason. All right, so here we have concentration is obviously decreasing over time. Okay, and that would mean the reaction should be getting slower because if the concentration goes down, the reaction rate should drop. And if we look at here, we still have NO2. So the end of this graph may not be the end of the story for this reaction because there's still reactant there. All right, if we take a look at these beakers, just doing a little bit of particle diagram analysis. All right, if we say that this one over here is 2 molar, all right, we want to figure out the concentrations for the other ones. So this has 8 dots. All right, if we take a look, this one also has 8 dots in it, but it has twice the volume. So stop and think about what would that mean if you have the same amount of HCl, but you double the volume. Put a number on your paper. Okay, hopefully you put a 1. Right, 1 molar, all right, twice the volume, half the concentration. All right, this one has the same volume as the 2 molar, but it has twice as many dots. All right, so stop and think about what that would mean for the concentration of this third beaker. Right, same volume, but twice as much stuff. Should have 4 molar there. All right, and then this one here, all right, if we notice, this one has the same number of dots as the 4 molar. Okay, it has 16 dots. All right, but it also has double the volume. So there's a couple of different ways you can approach this one. Right, you can also compare it to how many dots per 50 milliliters here. All right, this one now looks the same as this over here. All right, so however you approach this, you should be able to see that this one's going to have the same concentration as this 2 molar over here. There's just more of it in the beaker. All right, we're just using a little bit more of that exact same concentration. So I want you to make a prediction here. If we put a piece of magnesium into each beaker, all right, the pieces of magnesium are the same size. All the beakers, even the 1 molar, has plenty of HCl to fully react with the magnesium. I want you to take a moment, identify the fastest reaction, identify the slowest reaction, all right, and do you think that the remaining ones, are they going to be at the same speed or is one going to be faster than the other? Actually, write your prediction on your paper. I see some of you still resisting that. Did you write fastest and slowest? Okay, I hope so. See what happens. So 4 molar disappeared first. The 2 molars went next. And then the 1 molar is taking longer. This is the lowest concentration, right? So we had the 4 molar went fastest. This one went slowest. And then the 2 molars were the same, okay? It doesn't really matter that you have more of the 2 molar here, all right, and you have over here, they're still going to go about the same rate because 2 molar is 2 molar, okay? All right, quick note about surface area and concentration. They're not the same, all right? They both are going to affect the frequency of reactions. You saw that about surface area in the last video. But surface area is all about access to the reactants. It affects the frequency of the collisions because more particles are accessible to be collided with. But in a solution, all your particles are equally accessible. They're not trapped in the middle of other things in the same way with a solid. When you have surface area, you have particles trapped in the middle that the other reactant simply can't get at right away. All of your particles in a solution are equally accessible. So how long it takes is going to depend on how long it takes those dissolved particles to find the other reactant. So it's more about the spacing or the distance. If you have a dilute solution, your particles have farther to travel before they're going to hit that other reactant. In a concentrated solution, the particles are going to be like right there by the other reactant. So you don't have to go very far, you don't have to wait very long for them to collide. So even though these both affect the frequency of the collisions, they do so in different ways. All right, last thing here is temperature. All right, if we increase the temperature, think about that, we'll make the particles move faster or slower. Would that make the reaction occur more quickly, less quickly? And there's 2 ways that it impacts this. I want you to look at those options there for a moment. Think about which 2 ways can increasing the temperature impact the collisions. Okay. All right, so we know that when the temperature goes up, particles move more quickly. We did a whole unit that revolved kind of around that. All right, that'll make the reaction go faster. All right, you saw that in the demo video as well. The hot water clearly went way out of control compared to the cold water. It was going much faster. All right, there are 2 reasons for that is that the molecules are going to collide more often. Right? If they're moving faster, they're going to hit more frequently. Okay? But in this case, when they do hit, if they're moving faster, it's also going to be a harder collision. So there's going to be more energy in those collisions, which means they're more likely to meet that minimum energy requirement. Right? At a cold temperature, your particles are moving slower. So even when they do hit, they might not have enough energy to actually break the bonds, get over that energy diagram hill. All right, but at the higher temperatures, they are much more likely to have the energy to break those bonds. All right, that's just a little visual, low temperature versus high temperature, getting that idea of that particle movement in there. Okay. And also a skee ball analogy here for you, right? If you consider the top of the hill on your energy diagram, all right, when we say the top of the hill here, all right, top of the hill, right there, think about that as where the board has the 50 and 100 points are, all right, in skee ball. If you roll too little energy, you won't make it to the top of the hill. So maybe you'll hit like the 40-point mark or something, but it's not going to cause a reaction, okay? It's just going to end up, in this case, coming back down. Analogies all have their limitations, right? If you roll with enough energy, you could get it to the top of the hill. But how you have it oriented is still an issue, because just because you made it all the way up there with your skee ball doesn't mean it has to go in the 100 or the 50s up there, because, or the 50 or the 100s, sorry, because it might not have had the right orientation, right? So we know that just because it has enough energy doesn't mean there will be a reaction. All right, so I do have these links to these YouTube videos. You can see in the first video, the guy playing skee ball there he's not rolling the balls with a lot of energy. So he's scoring points, but he's not getting the reaction. We're saying that the reaction is you have to get it into the 50 or 100. All right, and then the second video, all right, that guy is rolling with more energy and mostly having the proper orientation as well. Okay, so if you want to watch those, especially for those of you who are still going, what's skee-ball? What is she talking about? Check out those videos. Okay. And quick little summary. All right. You can pause on this slide and write down whatever you need to. All right. But this is just formatted differently. All right. Affecting frequency of collisions. We have surface area, concentration, and temperature. All right. Affects how often things collide. The catalyst affects who collides, like who needs to collide with who, but it does not affect the frequency of collisions. Okay. Affecting energy of collisions, we know that catalysts will lower how much energy the collisions need to have. We know that increasing the temperature makes it more likely that they have enough energy. So both of these are affecting the energy of collisions, but in very different ways. Okay. And then catalysts are the ones that might affect orientation, all right? Your enzymes particularly will actually just help out with it. It doesn't change the orientation that is needed for an enzyme, but it helps provide the proper orientation. Okay? And nature of reactants, think of that as it's hard or it's impractical to alter the nature of your reactants. You can't do anything about complexity, right? If you try to take a complex molecule and make it a simpler molecule, you just have a different molecule that's not the same reaction you're going for anymore. Okay. Sometimes you can do some things with states of matter, and sometimes that's just not practical. Okay. So for those things, we don't really tend to mess with those as much. They just are what they are. Okay. And if you need entertainment, all right, this is sort of just the how to teach a 5-year-old how to play skee-ball, what that sounds like. I'm not going to read all of this, but if you want to pause it and read it for just your own entertainment, you are welcome to do so.